So I think we can start, but thank you very much. I'm very pleased to have the chance to introduce you to Professor Korobenko, Artem, who is visiting us again. And this has been organized together by Professor Antonio Huerta and myself. And I decided to introduce him today. Artem, originally from Ukraine, and long time living in North America, US, now Canada. PhD in computational mechanics from 𝗦𝗣𝗘𝗥𝗔𝗖𝗧, Tom Hughes student, so he comes from the variational family of computational mechanics and beyond. And he is a very active researcher with the foot in America and foot in Spain, in Europe, also in Spain. He will visit some of our conferences, like Coffee Progress, like Atmos and others. And we have actually a plan with the director that he will, this visit will reinforce the cooperation also in the framework of programs that Canada has to support the students. I have mentioned this to my this group of researchers that they should contact you if they have a interest in.
I'll say a few words at the end as well.
And then nothing else. Thank you, Artem. The title of the lecture is very explicit, and this is something why we ask him to talk about, because this is a topic of interest, not only in the context of the marine computational and marine engineering that we do at CIMNE, but also perspective of new programs in the naval industry, or offshore wind turbines and oil and gas.
Yeah.
Artem, thank you very much.
Thanks so much. So first of all, thanks again, thanks Antonio for organizing this. It's always great, every time I visit Barcelona, to come here and give a talk. So that's kind of a big split when you have one foot in North America, one foot in Europe. So one down would be jealous, for that. I would like to say first a few words about myself, about what our group is doing, and then come back to the topic. So as Eugenia mentioned, I did my undergrad in aerospace, and then as a Fulbright scholar, I moved to US. I did my MSc in mechanical engineering, and then I did my PhD in structural engineering with specialization in computational science, engineering, and math. And now I'm a professor at mechanical and manufacturing engineering. So it's like quite a different spectrum of everything, but behind that is computational engineering and science. Okay, that's what we do. I also spent sabbatical last time. This was the occasion I was able to visit CIMNE. I got a Humboldt fellowship, and another few hats I'm wearing. I'm the current president of the Canadian Association for the Computational Science and Engineering. Again, those of you who attended WCCM in Vancouver, you might remember me if you paid attention to those people speaking at the podium. And then I'm also the co-director for the University of Calgary Aerospace Network. So it's a group of faculty members, overseeing the aerospace and defense-related topics within the institutions in Western Canada. So again, we're a pure, computational group, and so I will tell you what I'm not gonna show you first, right? And if you're interested, we can follow up. So last time I visited, I got a privilege to talk about wind energy stuff. So kind of the top part of my, of the slides, with working with the atmospheric boundary layer flows, flow in the complex terrain, wind farm modeling, etc. And then on the other spectrum, we're working with the high-speed flows from the low subsonic, like eVTOL, urban air mobility, all the way to the hypersonic flow in the thermochemical non-equilibrium, like re-entry vehicles, and the plasma physics and all of that, and everything in between. So that's the beauty of the Navier-Stokes equations, how I try to motivate my students. And so today I will talk about the left part, right, of the slides, and which is kind of highlighted over here. So videos, because there are so many of them, so they will be a little jaggy, but this is almost exclusively the work related to the marine renewable energy system. So the hydrokinetic turbines, the vertical axis, horizontal axis, all the way from the single phase to the multi-phase cavitating flow. So I will show you, some very recent work we've done on that respect, and kind of highlight a few challenges and the ongoing perspective direction. Okay. So huge kudos to my former students. Ahmed Bayram is currently working in the Wood Consulting. He's the chief CFD engineers over there. And Mr. 𝗦𝗣𝗘𝗥𝗔𝗞𝗘𝗥 is also working in the industry in another company. So a few papers over here. And again, I would be happy to share the presentation because all of the results were published. So I can send you the PDF and you can have a better look and find all the typos and inconsistency and then send me an email with that. A very quick motivation about the work we do. It's, again, both from the civil and the military application, right, of the civil spectrum, the several, hydrokinetic concepts, right? I probably should have included one from Spain. I believe they're a very active, topic because, again, you're surrounded by the water, so it would be, make more sense. And then, the sports application, like all of those, like a flying hydrofoils, right, which has a very cool, the multiphase problem where it's not just the cavitation, you also have the condensation, right, which is the entering the air, which is, non-condensable fluids, etc. And then all the way on the military spectrum, some kind of same things, the flying hydrofoil, but of the different type of vehicles, and then, the ship propellers and specifically cavitation. And we are currently looking only from the fluid mechanics point of view, and you can see all of the challenges just doing fluid mechanics itself, right? High Reynolds number, multi-physics coupling, computational efficiency, etc. And then as you start adding the structural part, for example, if you want to look at the explosion or collapse of your cavity pockets, right, which will be almost like a blast on your propellers, which will completely destroy the surface, that it will bring another kind of the layer of fidelity, and that's something that we are looking for right now, but again, I'm not going to show this talk any of those. So there will be lots of equations, and so I don't want to apologize because you're all very smart people. So let's talk about what is behind all of these colorful pictures. Otherwise, they're just colorful pictures, right? So it's a very general form. So first of all, as Eugenia mentioned, I am coming from the finite element for fluids community. Again, for this group, I would not call myself a unique person because many of you are working in that realm. So that's what we do, and we start with the a strong form of the governing equation. So your classical conservation of the linear momentum, conservation of mass, and then you have the transport equation to govern your vapor or volume fraction. You decide which one you want to solve for. And then you also have the free surface. And so for the free surface, we're using the level set function. So this psi represents the level set, okay? For the multi-phase, so it's the homogeneous mixture model, right? So the classical equation for that one in terms of the Heaviside function, so nothing exotic. I will also mention the pros and cons of this homogeneous mixture model approach. Pros, it's very simple and straightforward. Okay, cons, it relies heavily on the empiricists. Okay, because as you will see in the equations, you need to have the proper rate for the formation of one of the phases, right? So you need to somehow assume a specific cavitation number, which I don't want to do because in the reality, give me a system and I model it, and it will give me whatever it should. So this is where we've done this. It works. It's perfect. But what I'm looking for right now is to do something like the Cauchy-Hiller type of equations, right? Where you can actually solve for the cavitation without assuming any empiricism. And again, we kind of inspired the work of Hector Jimenez Hector Holmes, sorry, is doing at Purdue, so where they implemented that. So that's kind of the future steps. And again, of course, you need to have this iconal equation, right, to make sure that you're solving for these distance functions, okay? Then we'll try to massage a little bit the equations to make them more programmable in that sense, right? So we put all of the unknowns on the right side for the continuity equations. We rearrange the term in the advection diffusion equations. And so now you see on the right-hand side of this transport equation, you have this S file, okay? So that's your source term, which will correspond to the specific cavitation model that you are using, okay? And so I will explain what we do. And so the way we solve the iconal equations is, we kind of formulated this in the advective form using this pseudo time step approach, okay? So again, that's something that Yuri and Ido Ackerman done, many years ago, and many researchers first actually introduced that approach, and we successfully adopted that. Now, For the cavitation, right? So as I mentioned, we're using this transport equation-based cavitation model. Again, if you are in the area, you know that there are two, the most commonly used ones. So one is called the Merkle model. Okay, so this is the model where you express your source term, right? So it's some kind of like a linearity of which is the proportional to your local static pressure, right? And then the second set of model, and again, this is the empiricism that I'm talking about, right? So you have this rate of production, rate of destruction, which is then related to the cavitation number, okay? And then the second one is the 𝗦𝗘𝗘𝗥 model, which is kind of a simplification of your Rayleigh-Placé equation, okay? So it's kind of based on this single bubble dynamics, okay? Even though in all of these homogeneous mixture model, we are not resolving individual bubble, okay? So you're modeling the field. So it's, you may think about it like most appropriate application would be the, cloud cavitation, right? Because even when you go to the cavitation, there's a different regimes, right? Individual bubble, cloud cavitation, tip cavitation, etc., etc. So some of the models might work best for one or another. And so this is, again, this is the expression. Again, we did not invent this model. We just successfully adopted that in our finite element formulation. The very challenging task was to actually linearize this, right? Because you have a square root, and so how do you do that? So we did some approximation. It's actually in the paper, so if you're interested, please go ahead. And we actually perform a sensitivity test to a different linearization strategies, because if you linearize everything, right, you have all of these fancy Euler-Jacobian matrices, but some of them are actually not important. You can actually skip them. So for example, is your cavity or is your transport equation depends on the pressure? Like, can you ignore that? Can, but that will affect your rate of convergence, maybe affecting stability. So we actually did a very meticulous test and showed which linearization schemes works best in that respect. Okay. So, and again, this is the level of the empiricism, right? Because you need to know this rate of vapor production and destruction. You need to assume a specific, nuclei diameter and radius, etc., etc. So, I mean, it works, but I don't like that level of the empiricism. Okay, and yeah, this is where your reference pressure. You need to know the cavitation number. Okay, so the lower the cavitation number, the higher the cavitation you have. So that's kind of a physics of the cavitation at the level I want to present it here. Okay, good. So now you remember, hopefully, still that set of the governing equation, right? The strong form, right? Your partial differential equation. So now let's formulate the weak form of the problem, right? Using the variational calculus. Okay, so it's nothing but your integral form of the equation, right? So this is your classical Galerkin, right? Corresponding to the momentum, to the continuity, transport equation for the vapor volume fraction, and then your body term corresponding to the momentum equation. Then the same integral form for the level set, and the same weak form for the distance functions. Okay, so this is your standard classical Galerkin finite element approach. Good, unstable, in the presence of the source terms, in the presence of the advection dominated regimes, it falls apart. So you need to do something smarter on that. And this is where we go and we work with the stabilized finite element method, and more specifically with the variational multiscale formulation. So I will give you a very quick intro to the VMS method, which I assume many of you are familiar with. Like, how many of you heard about VMS or using VMS? Okay, how many of you know LES? Okay, how many of you are structural mechanics people? Okay, how many of you heard about the turbulence? Okay, excellent. Let's start with that. Okay, turbulence, right? The way you describe the turbulence, you can describe it using this energy cascade plot. Okay, so you plot the energy versus the wave number, right? Larger eddies, smaller frequency, more energy containing scales, and then what happens as these vortices propagate, they break apart. And so this is your energy cascade. So your energy transferred from the large scale to the small, and they dissipate at the Kolmogorov scales, right? So this is your viscous dissipation regimes, okay? Now, a very quick intro to the turbulence modeling. There is a three main turbulence modeling approach. One is called, RANS, or actually URANS, where you simply model everything. So you are not resolving at all. In URANS, you're only resolving your energetic large scale. Then the second one is LES, where you assume that your cutout length is somewhere in the inertia regime, right? So this is famous -5/3, right, slope. And then you have the DNS, where you're resolving everything, meaning that your mesh is so fine that you're capturing everything. So VMS is a LES-like approach, okay, which means your mesh should be in this inertia regime, okay? So that's the starting point. And then classical to LES, you start with this scale separation into the coarse scale, something that you are capturing with your mesh, and then the small scale, something that you are modeling. And so now you introduce that decomposition into your test function, right? And then you throw in solution variables and throw it back into your Galerkin form. So what you ended up with is the two set of equation, a coarse scale and the fine scale. And so now to close the system, I simply need to solve the fine scale equation for my U prime and then throw it back. Can I? Of course I cannot, right? Because it's as difficult as solving the 𝗦𝗣𝗘𝗥. So this is where the beautiful mathematics comes into place. And we can formulate these problems in terms of the Green functions, and then we solve for the approximate Green function. So lots of work done by colleagues here, Ramon as well, and others, Antonio, and many people. So what I will just show is kind of a simple form of that, right? So I will show the fine scale equation in terms of this projection operator, okay? So I can rearrange my terms so that all of the large scales will be on the right-hand side, right? And you will see that actually when I group them, they look like the residual of the large scale problem, for the momentum, for the continuity, for the advection diffusion equation. And then I have this additional term, these functions, which kind of enforce that my right-hand side is still infinite dimensional, right? Because that's what your fine scale is. Your fine scale subspace is infinite dimensional, okay? And so then you actually do the truncation, okay? So you approximate, you says, okay, I have my expansion, I truncate all of the higher terms, I keep only the first one. Is it good? Many people are still using just that one. So it's good enough, but I still want to look what is the impact of those higher order terms would be. And so you can formulate this approximate fine scale problem. Now, you still have a choice even here what to do. So what projections you will use? The simplest one is just the identity, okay? And then what you do with your small scales. Do you assume this to be quasi-static? Do you assume this to be orthogonal? So again, I refer to Professor 𝗦𝗘𝗔𝗞𝗘𝗥 work, right, who did an excellent comparison of both full order model, reduced order model with that respect. We're using the simplest one possible. So we assume it's quasi-static, and we assume it's just a simple algebraic model, okay? So pretty much your small scale is simply proportional to the residuals of the large scale, and your proportionality factor is your stabilization parameter tau, okay? Which has this diagonal term, and it kind of were designed to stabilize the formulation in the presence of the inertia dominated, advection dominated, when your diffusion term dominates. So again, look at the work from Tom Hughes and colleague on the origin of the stabilized finite element methods if you really want to get more insight into that, okay? So now, with all of that explanation about the small scale, so now you can actually say I know turbulence, I know the basics of the stabilized finite element method. So the next year I will come and I ask how many of you know turbulence and VMS. You should raise your hand, because I remember all of you. Okay, so let's put all of the terms together, right, and formulate our problem. Okay, so as before, nothing happened to the Galerkin terms; they're still there. Okay, but now you have an additional term. What are those? When you introduce these decompositions, now you have an interaction between your large scale and small scale. So you have the terms which will look like U prime, U prime U, U prime U prime. Okay, if you compare it to the classical turbulence modeling, they will look like your cross stress term, Leonard stress term, and the Reynolds-like stress term. I would like to add this Reynolds-like stress term because every time I talk to fluid mechanician, I say this is the Reynolds stress term. They get hammered, okay, without explaining too much. So I like to add this line. Okay, so what does it look like numerically? Okay, you have your classical streamline 𝗦𝗣𝗘𝗥. So this is your cross stress term, U prime. Okay, so you take the advective part, and you stabilize that one. Then you have this additional PSPG term, pressure stabilized Petrov-Galerkin, to satisfy Babushka-Breze condition, and so that we can use the equal order interpolation for the velocity and pressure. Okay, Then you have this additional term on the which represents your continuity least square on the incompressibility constraint. And then you have an additional VMS terms, which is the another cross stress, right? This is your, if you call that one UU prime, this would be your U prime U, okay? And you have this Reynolds-like stress term, okay, which is the interaction between the small scale. Okay, so you have that for the momentum, you have that for the transport equation, here, again, I don't want to go too much into the details, but again, for the type of problems we are considering, stabilization itself is not enough, so you need to enforce additional discontinuity capturing. So this is the classical gradient-based discontinuity capturing that we need to enforce, and we need to do that for the momentum, for the transport equation, and for the level set and redistancing, okay? So that's what you will have. So again, I showed you the momentum and the transport equation couple. So we solve them as the couple problem, right? And then it will be followed by the level set, right? So this is your VMS formulation for the level set equation. Again, nothing but the Galerkin plus SUPG plus discontinuity capturing. And then you do the same thing for the redistancing, okay? So it's your classical Galerkin, SUPG part, plus discontinuity capturing. Now, for the distance functions, we also realized that when we solve it together with the level set, right? Because we affect that. Sometimes we might lose, some stability, and so we actually enforce this additional penalty, during the redistancing step. Okay, and your classical right-hand side. Okay, so those are the equations. Now, a few more ingredients that we need to implement. So for the type of problems we will be considering, which is kind of represented here on this schematic view. So think about you have your turbine, right? It rotates, and then the rest of the domain surrounding that is stationary. Okay, so we use something called the sliding interface approach, right? So the domain which encompasses rotor rotating, the rest of the domain keeps stationary. So what you need to do, you need to enforce your kinematic and traction compatibility on those boundaries, right? In terms of the fluxes, in terms of the other variables. Okay, so you can think about this sliding interface operator either as a discontinuity or discontinuous Galerkin method or Nietzsche's-like method, right? So the same idea that you would do that. So you will have the term which will look like consistency, adjoint consistency, and penalty term. I'll just leave it there because I don't have much time to go into this discussion, but this is how they look like. Okay, looks quite messy, but indeed, what you do, you are enforcing this compatibility. Okay, on the interfaces for the velocity, for the volume vapor fraction, for your level set, and then you need to do the same thing for the distance functions. And so for the distance functions, if we treat that operator as the advective term, we actually realize because like that combination together with the discontinuity capturing doesn't quite work well, okay? Because we start seeing instability far from the boundary. Okay, we remove discontinuity, it's stabilized everywhere, but we start seeing issues close to the interface. Oh, actually, it's other way around. Yeah, because discontinuity capturing specifically, everywhere. Okay, and so the way we treated that problem is we actually treated the redistancing as the diffusive term. Okay, and so we added just an additional terms, and then it actually worked quite well and stabilized. Okay, so. And we tested this like a toy problem. So we put a fictitious domain and we put this wave breaking problem through that fictitious domain, and it smoothly went through it without introducing any artificial instabilities and whatsoever. A few more ingredients, because we don't just simply work with the uniform inflow. We used to do that in the past, and then we realized that everything is turbulent in nature. So we need to somehow impose this turbulent inflow. So there are many ways you can do it in practice. You can do this recycling method, right? You can do kind of this fictitious domain or precursor simulation, where you run the precursor, you generate your desired statistic. When you reach that, then you kind of feed in the domain. We prefer this synthetic turbulence generation method. There are actually three that I'm aware of. So STG is one. Then there is also SME, synthetic yeah, so there are some other synthetic methods, just the way you enforce this randomness. But the idea behind this synthetic turbulence generation is also given in this paper. So it's based on the idea introduced by Schur in 2014. Okay, so you kind of want to represent this fluctuating velocity vector, right? So you kind of rewrite it in terms of this matrix A, and then you do the Cholesky decomposition, right? So in terms of this Reynolds stresses, right? And then you try to, by assigning these different random parameters, to kind of mimic, that Reynolds stresses that you would see in the flow. I mean, what you can actually do, let's say, what is your turbulent intensity, 5%, 10%, etc. You can relate that one to your Reynolds stresses or your turbulent kinetic energy, and then you relate it to the Reynolds stresses, and you kind of get what you want. Okay, so pretty standard methods, nothing exotic, but the unique thing about this, it was actually the first time the STG was implemented in the stabilized finite element, and we actually implemented that into the isogeometric analysis, because we're also doing IGA for fluids. So it's not just finite elements, we're also using NERDS or B-spline to model the fluids. Why? Higher order continuity is always great, but then the bandwidth increases drastically. So that's why I'm, IGA is still good, but there are still more work that has to be done to make it on more commercially viable scales. Okay. Good. Finally, now let's go to the applications. Again, I might skip some because I don't want to run too much over time. So the first problem to show. So this is the work that we started with a company called New Energy Corporation. This is the Calgary-based company. They're the world leader on the commercial hydrokinetic turbines using this vertical axis concept. So the good thing about the vertical axis concept is the omnidirectional. Doesn't matter where the flow coming from, it will rotate. The bad thing, so when your flow hits your first turbine, the wave generates, and then when it rotates, the same blade will hit its own wave in the downstream region. So what happened with the vertical axis turbine, hydro, wind, doesn't matter. Your flow is changing from the fully attached to the fully separate within a single revolution. Okay, good luck to model that. Like that really put a huge challenge on the turbulence modeling in general. Okay, and so here we actually, this was the design that they provided us, and this was the final design that we came up with, which was 15% more efficient than the original one, and I will show some tests. Again, just the characteristics of the turbine itself. I don't want to go too much. So this was, I believe, 5 kilowatt on the previous slide. This was a 25 kilowatt prototype, and they also currently have 250 kilowatt prototype that they are testing in the Bay of Fundy. So if you're working in the marine area, you know that this is the site with the largest tides in the world. So you can have a 30-meter tide, which will change. So that test site it's in Nova Scotia in Canada. So it's pretty cool. But then you don't want to just simply put that system in the water and make it an artificial reef. Right? That already happened. We already have one which is sitting over there. And so this is where the numerical simulation really comes as the handy tool to inform your experiments. So that's what I'm seeing, as impact. We are not replacing experiments. We are informing experiments, and we're creating this, a dynamic loop where, one can run another. Experiments can inform numerics as well, right? Why not? Some basic tests, which I can probably skip. Again, when you do a CFD, you want to make sure that you first do validation and verification, right? You show the grid convergence, you show that you're agreeing with the experiment. So, this is the work we've done. We look at the power production, and we look at the wake to make sure that, as we refine, there is nothing. You see actually that the wake is actually non-symmetric, and that's because of the rotation. So as your turbine rotates, depending on the direction, it will skew the wake in that direction. So it's pretty interesting, which also has an implication on the stability of your free surface, okay, and how your wake will meander. And if you put multiple units next to each other, you can actually, do an optimization problem to steer your wake such that it would not hit your downstream turbine. Speaking about the downstream turbines, right? So we did simulations with the multiple units, and the video is a little lacking. I apologize for that. The one on the bottom should also play. We'll see if it does. But it's just a different view, nothing crazy. But for this test problem, we also did the multi-domain approach. We're like, why we need to simulate two turbines in the same computational domain? Can we just run a single turbine, collect the data, and then run the second turbine? And so this is this idea behind this multi-domain approach, which I just explained. You run the first turbine, you collect the data at the plane you want to, and then you can play with the distance without actually rerunning anything. So I simply like collect the data here, and it will give me a larger distance between the units, right? So with this multi-domain approach, you can play with the distancing. Now, I should mention that there are two ways you can do that. You can either do interpolation, which is the simplest one, or you can do L2 projection, which is more accurate but more slower one. We just picked interpolation, and the error was pretty negligible. So here is the comparison. Again, actually, the comparison between a single domain and multi-domain I'm not showing. That actually matches quite well. You can check that in the paper. But here we tested the different distance. So saying that what if you put the units 2 diameter versus 4 diameter downstreams, okay? So comparing to a single turbine, if you put the units 2 diameters apart, you will have a 23% deficit on your second turbine. If you put them 4 diameters, you get 9% deficit. So now if you think about if you want to put them on the single bar, the distance is pretty minimal. So your second turbine will really suffer and will underperform, which will affect your loading on the generator, fatigue, et cetera, et cetera. So if you just design your unit as a single system, you screw it pretty much, okay? Because you're not accounting for that 23%. I will skip through this one because we also look at the effect of the turbulence inflow. So we varied the turbulence intensity, like 5%, 10%, and the uniform, right? And we look at the wake recovery. So, one thing is you increase your turbulent intensity, you increase your mixing, your wake is recovering faster, right? So which is the good thing, so which will allow you to put units closer to each other, right? So you actually can artificially increase your turbulent intensity by some kind of a passive control, some kind of narrow channels or some mixers or etc. Okay. And what we also did, we look at the effect of the immersion. So this was actually a simulation done with a free surface, okay? And we look at something called the deep immersion versus the shallow immersion. And we look at the different struts. So we look at the different geometrical parameters of the turbine. When the struts located at the quarter span and when they're located at the tip. Because from the fluid mechanics point of view, when you have this junction, like this vortex, which is forming at that junction, will pretty much would be responsible for the deficit in your power, right? Because every time you have this blade wake interaction, that drops your performance, right? So you ideally want to steer those wakes kind of away, okay? And so when you put the struts at the tip, right, you still have a formation of the tip vortex, but that tip vortex kind of leaves and would not actually interact much with the blade. However, from the structural point of view, you have a doubly supported beam, so your vibration that you start to encounter on the blade can be significant. So we didn't look on that one, but this is kind of the next step, like from the structural point of view to see what happens. Again, we also look from the free surface, when you have the shallow immersion versus deep immersion, what happens to the stability of your free surface. So this was just a still water, but we can also impose the wake, using the different wave spectrum. Sorry, wake. We can impose the different waves using whatever wave spectrum we would like to do, or maybe even like some kind of piston generation approach for these wakes. A few more interesting studies. Let's see. Okay, 6 minutes. So I put 38. So this will give me a buffer of about 6 minutes, which I can go over. So far everything was, here's the numerics, believe it, okay, which you should not, okay, be always skeptical. And so what we did, we went to this experimental test. I believe it was either in Manchester, if I'm not mistaken, on this. So there are two test cases. One, which is done in the cavitation tunnel, right, and another one which is done in the open tank, such that you can model the free surface. The experiments is such a beast that you cannot experimentally model both simultaneously. You could not model cavitation and free surface experimentally, okay? Because you would not be able to get that level in the open channel, okay? Unless I don't know what you need to do with the whole room where the open channel is, how you need to compress that, okay? So we did that separately. Okay, so we separately validated the cavitation, we separately validated free surface, and then numerically we ran it both together and showed what is the impact. So you see all of the characteristics, you see the mesh. Again, for this purpose, we use this multi-domain approach, the sliding interface approach. You actually saw in one of the test study where we look at the effect of the turbulence, we actually didn't use the sliding interface. It was a single domain which rotated itself. My students were very skeptical, they didn't believe it will work, and it did. I was also quite skeptical, like, can you impose the time-varying boundary conditions on the rotating domain and pretty much got everything nice and smooth? And the answer is yes, you can, okay? But here, because the problem is more complex, we use this sliding interface. Okay, so the video's somehow playing. We still have, okay, this actually may be better because it will give you more time to see what happens to the flow physics. Okay, so a few things. First of all, a pure vetted case, okay, when there is no cavitation, no free surface, and we see how good we are in predicting power and thrust. Okay, and you see, we are pretty much within the experimental uncertainty in that case. Okay, then we went to the cavitation. Unfortunately, they didn't have any quantitative data for the cavitation. However, they had a qualitative data. So what are we comparing here is the formation of the vapor cavity on the 15% of the tip of your blade. And you can see we are comparing what we're getting with our cavitation model to what they're seeing at the experiment. Now, our mesh resolution is not that fine. That's why we're not really capturing this tip vortex, right, which is forming. So for that one, you probably need to do some kind of adaptive mesh refinement and really track that formation of the vortices. But even without that, the results are pretty good. And you can see in terms of the deficit, okay, so you see the reduction of almost by 32% in CP when your cavitation is forming. Only 15% of the tip of your blade, and you have a reduction in power by 32. Okay, if you did not account for that, and you put your system in the water, and there is a cavitation which is triggering, again, you screwed it, right? And then you need to take the unit out of the water, and you need to modify that. Now, cavitation, not always bad. If you look into the medical application, cavitation is good. Because, for example, if you look at the ultrasound hitting the kidney stones, that's kind of a cavitation problem that you're also dealing with, right? Some others, right? So sometimes enhancing this mixing through the cavitation is good, but not for this system. Then we did a standalone free surface, okay, because they had the open tank experiments. And again, we are comparing CP and we are comparing CT. And again, the results matches quite well. Now, I would also like to point out that I'm a little bit skeptical about their experimental measurements because for some reason, their CT for the vetted and the free surface case is identical. Could be, right? But because they kind of do not really investigate the uncertainty too much, when they did those tests, it's still an open question. But again, apart from that skepticism, the results matching pretty well. And now we merge them together, okay, and see, how much deficit you will have. I actually would like to mention that when you have only free surface, the deficit in the power is about 8%. Okay, so now when you combine both cavitation and free surface, your probably best guess is just a linear interpolation. I take both and just combine them, and so my deficit would be either both combined. But again, it's a nonlinear problem, so that's not the case. And so when you combine them, and this is actually the video playing here. So first of all, when you have the cavity, you see how your flow is changing. So you're kind of developing this horseshoe-like vortices, which originates from your tip, right? That also breaks up, the downwind interaction, okay? It affects your free surface, etc. And the power deficit that you see when it is coupled is about 37% in the reduction. So again, pretty significant, not as bad as when you just simply add those two together, but still something that you could not neglect, okay? Now, something that we've done in the past, but I did not have time to talk about in this study, is we also work on different fluid structure interaction problems, as well as more like a classical hydrodynamics problem. So on the lab, that was an early work we've done when I was still in the UC San Diego. It's the flapping hydrofoils. Okay, so it's like a copycat company where they put this on the kayaks, and so you like a paddle, and then you're creating the propulsive force, they push you forward. And so this it's a flexible hydrofoil, so we kind of mimic the material model to be like a rubber-like material, but it also has a stiffener, which has a very specific zigzag pattern. So, we accounted for that as well. Then, on the very large scale, we did an offshore floating horizontal axis wind turbine with the mooring cables. So here, all the structural components are modeled with Kirchhoff-Love shell. Okay. Again, back in the days, Dave Benson and Yuri did the test, and they compared Reisner-Midland with the Kirchhoff-Love. They showed that Kirchhoff-Love still is, applicable for these regimes, even though you're actually ignoring that cross thickness through thickness, stresses. Again, the Euler-Bernoulli beam is used here to model the main shaft as well as the mooring cables. And then we have the waves. So again, the whole system is moving with the waves. It was in the parked condition, so it was not rotating, but we could have also done that one. And again, some classical hydrodynamics problem on the propeller. Again, looking into the cavitation as well as the ship hydrodynamics. So this is the famous JBC, which is Japan bulk carrier. Like if you go to this, marine engineering, this is, I believe, a case study. They look quite extensively. So now, I want to take maybe an extra, 3 minutes, let me put it this way, and kind of show an ongoing work that we are doing. And this is the talk I will be, or similar talk I will be giving at the couple problems recently. So far, I showed you a CFD at the very high fidelity where we are resolving the surface. Okay, it's great, it gives you all of the details, but it's damn slow. Okay, it's not practical, period. Okay, it takes a lot of time unless you do something smart with your architecture or even simulations, whatever, right? So the idea that we adopted from the wind energy community, and we successfully tested that for the wind engineering application, which I show over here, is use something called the actuator line approach. So the idea behind that, can I actually represent my airfoil as the point load? The answer is yes, you can, okay? So what you do, so think about just a 2D as an example. So this is your blades. And what you do, you split your blades into the different sections, okay? At every section, you know the information about your geometry, you know the chord length, you know the airfoil type, you know the lift and drag versus the angle of attack. You use that one, okay? And then you collect your forces. You probably could not see it, but you see where this element is located. I want to use the analogy. This is the lowest fidelity immersed method. Let me put it this way, okay? I don't know. People in the immersed community probably will kill me, but yeah, kind of like that, right? You have a point which is immersed in the, external. So you collect the velocity, and then you use the blade element momentum theory to calculate your aerodynamic forces, okay? And then you take that aerodynamic forces and you put them back on your background grid as the source term in your momentum equation, okay? And you kind of, again, because it's just a point, you could not just simply put a point load, you need to smear it out, so you kind of project it using some kind of Gaussian distribution function, okay? And then you repeat that for every point as the turbine rotates, and what you get exactly this. You correctly represent the wake which is forming, with your structure without actually resolving your structure at all. So significant speed up. And we currently, just recently actually, tested this ALM approach for the vertical axis. And you see this is a comparison with some studies, but again, this is very preliminary. And we've done this for the air, the same thing we can do for the water. And this is something that we're currently testing. Now, another thing that we are working on, and this would be another talk I will be giving when I'm back here for the Atmos, is the reduced order model. Okay, so I put it, again, there are many people in the room who are working in the ROM, okay, classical, POD-based ROM, okay, with your classical quasi-static algebraic subgrid scale model for the FOM. And we're using something called the consistent ROM, which means we incorporated all of the stabilization that we use in FOM. It's well known that your ROM will fail in the high Reynolds number. I was always quite skeptical about that. And I just out of curiosity, we decided to run this problem. So here It's the wind turbine operating at the Reynolds number of order 10 to power 7. We were able, with the mesh-based hyperreduction, to represent the wake using only 10 modes, and it was stable. And you look at the L2 error for your velocity, for the pressure, it was an order of 10 to -3, 10 to -2. So the results were pretty impressive. So the paper is currently under review in the CMME, but I would be happy to share the data. So the same ROM we try to implement for the marine. So that was the last technical slide. So just a few farewell slides to mention, as Evgenia pointed out. These days, there is lots of opportunity for collaboration between Canada and the EU. Canada can participate in the Horizon funds. We can link the Horizon funds. They sign an agreement between both countries. Also, we have a mobility program, which is funded by Canada. So I can send students to Spain for 6 months, fully funded by Canada, and I can host students from Spain, fully funded for 6 months by Canada. So that's a win-win situation, in my opinion. And so also, again, we have lots of open positions. I really like to work with people who came from the European system, because same mentality is easier to work with. More direct. I'm very bad at this Canadian sandwich approach, where say something very positive first and then very bad, critical. I'm always going to very critical stuff first. I'm trying to change. My wife helped me with that. But if you have some very smart undergrad students, who would like to go outside for some reason, we have a fully funded position for that, for both MSc and PhD. So our MSc is also fully funded at the same level as PhD. I will just leave this statement from Van Neumann, and thank you so much for your attention.
Yeah, I think your lecture, I will consider it within the framework of classical computational mechanics. You didn't use artificial intelligence word in your lecture, which I really appreciate. I'm sure this has been also a test for our students, because this is the core group of computational mechanics.
No one fall asleep.
You could believe that now there are people working working in the university, even in our environment, that they finish thesis in computational mechanics and they don't know what final elements are. Anyway, but using data-driven computational mechanics. This was great to hear what you tell us, and the floor is open for comments or questions
or critics, anything. Like, it's very informal, very informal. If you don't like something or you think wrong, something is wrong. Let's discuss that, because everything is work in progress, right? Kind of.
I would like to squeeze my question first before I have opportunity. Something you didn't mention, it's very technical, it's about time integration.
Oh,
time integration, and this is related also because you are solving the nonlinear system of equations. Time integration and any iteration in the process.
Yeah. So for the time integration, this is the generalized alpha, second order accurate implicit, right, unconditionally stable. Then on every time step, we are solving the system of nonlinear equation with the Newton-Raphson method. Okay, so then we come up with all of these Euler-Jacobian matrices that my students love to derive by hand, and you can do automatic differentiation if you want to. And then on every nonlinear iteration, you're solving the linear system of equation with the GMRES. So with the sparse GMRES, which is your classical, Saad and Schultz implementation. We actually took their paper.
How many iterations for this next turbulent?
Yeah. So for the time step, again, it's a problem dependent. For some of the turbine with ALM, is like 10 to -1, 10 to -2. We can always test that. Again, it's still not adaptive time stepping, so there is always a room for improving. About nonlinear, we are converging probably within 4 to 5. So this is again about 3 orders reduction in your residuals, right? Normally the pressure is the hardest one, right? Because that's very steep, and at the second one you will see that. And then for the linear iterations, depending on the problem and the stiffness of the problem, like 50 to 100. So again, and that's the trade-off. You can sacrifice your linear to have maybe more nonlinear, or you sacrifice your nonlinear. So you start playing, and everything is a CPU-based. You might get some benefits if you start doing hybrid GPU-based. I've been told that it depends. Actually, I thought GPU is the way to go, but I've been actually proven wrong. So some cases actually would not give you any benefits, just the harm. So because you need to actually convert your whole code to GPU. You could not just simply say, oh, I'm using OpenACC with my 𝗦𝗣𝗘𝗥, right? Because yeah, you have 70 gigs within GPU and then 7 CPU to GPU, so you screwed, right? Sorry, it was not a short answer.
We discussed run out
Linear elements, or will you go high?
Excellent. Yeah, just linear. Yeah, so classical linear finite elements, simplicity. We always been pointed out, especially when we're doing IGA, and we're comparing IGA, which is the quadratic, to linear firms. Like, oh, that's unfair comparison, which I totally agree. I agree, right? So there you need to go to a higher order. So I haven't done that yet. I would love to. Again, just because our math generation we're using commercial beta tool. So, but if someone can give a high, technically like the formulation is suitable for that. We don't have to change actually much, like because the size of your linear system will increase. But I think that can be done automatically. It is an in-house code, so very user-unfriendly. Okay, but we would like to at some point find the suitable platform where we can put it in. So far, it's just in-house.
I have a question and a comment.
Yeah.
The question is, in your sliding mesh technique, do you use matching meshes or not? Because if you introduce the niches term, you have the complete freedom to use any.
It's non-matching.
They're non-matching.
Non-matching.
So
And
it's not the original one.
No, it's a non-matching. So we build separately for the inner volume, separately for the outer. Technically,
do you allow for an intersection between both?
Sorry?
Do you allow for an intersection between?
Oh, no. It's not non-overlapping.
It's non-overlapping.
Non-overlapping. No, so you have a common interface, but the nodes are sliding with respect to each other.
But you don't adjust the time so that.
No. I mean, yeah, like we didn't perform a careful study, but yeah, we haven't seen much effect on the time step, for that purpose. But yeah, you don't want to slide too much.
Right.
But it depends how frequently you're actually doing the update.
I guess with your turn, with your niche-like terms, you don't need to have matching meshes.
No, they're not matching, and that's
they could even overlap.
They technically can, so kind of chimera-like approach or overset grid. Yeah, but you just then need to, instead of coupling at the surface, you need to really deal with the volumetric and kind of avoid this ghost element which is shared maybe. But
if you have overlapping there, no.
Yeah, well, could be. Yeah, and actually the same niches approach we use for the FSI, and there it's even a different discretization scheme. So one was the IGA, another one FEM, and so we do the same niches coupling on the interface.
And then the second question was, in fact, I would like to know if you are aware of any formulation for cavitation that is more, let's say, based on physical principles, and in particular using dispersed multiphase flow models.
Dispersed multiphase. Not from the top of my head. Again, the work that Hector is doing, but again, he is solving, I think, computer.
Yeah, but that's again.
It is still this transfer-based approach. I believe he actually just recently published a paper in CIMNE on the dispersive cavitation model. I think it's called something 𝗦𝗣𝗘𝗥. I forgot the name, but yeah, I'm sure people done, right? But yeah, we just went with the simplest one, to be honest, right? To just test how that performed. Now, I would like to go away of that empiricist. So that's what I don't like. This is where, these models would be very simple.
Thank you. Thank you for the talk.
Thanks.
Any other comment, question? Remember, Professor Korobenko said he reminds the faces. Question. So you can contact him directly for any question or proposal of these short visits that he will surely will answer. And I think you raise your hand for your last last question.
Yes. I was curious about the results in which you researched about the impacts of multiple vertical axis turbines, I think it was. And you said with your multi-domain approach, you were cutting at different positions to set the distance.
Yeah.
I guess you were neglecting the impact of the second turbine on the first turbine.
Yeah. So the upwind effect, right? Yeah. So we actually did the test because we also ran the simulation of the both turbine on the single domain. So the upstream effect is negligible. So for that case, okay. Now, if you have some rapid changes in your flow, okay, but normally, like you think about, you put this into your river application. It's a unidirectional flow. There is no reversal flow for the river, right? And so there, yeah, there would be not much effect on that. Okay. Yeah, I mean, there's always some error. Like numerics, there's always error. How acceptable your error is. In our case, the impact of that error was way below the threshold. So
it was interesting because we recently had a problem. It was not hydrodynamics, but aerodynamics, and we did find a very unexpected physics phenomena because of upwind.
Yeah, your pressure, like just yeah, exactly. You're talking about the wind.
Yeah.
There your pressure rise, right, due to the impacting. That will have way more effect, right, compared to this. Again, different, fluids, right? So that's why that upstream effect and the way your pressure is actually propagating in that media is way more pronounced. So for the wind farm, I believe on my first or second slide there was a picture. We're doing the whole wind farm, like a several by several kilometers. I used to be also the Canadian lead for one of the IEA task force for the joint assessment models, where we look at this, how you place the turbine. So there, yeah, you would see effect, in short.
Since we are lucky to have the director of CIMNE, Javier, would you like to say?
Well, I would like to thank you for taking the time. I know that you're doing a circuit of a number of conferences in Europe, but it's great that you took the time to come over to CIMNE, stop and spend some time with us and give this seminar. We would like to invite you to come again in the future and perhaps spend a little bit more time.
Would be happy. Absolutely.
Spend a month or a little bit longer so that you can collaborate a little bit more extensively with the people in CIMNE. And this offer of the Canadian government actually paying for our students to be there, and one of them coming up here, sounds like a fantastic offer, and I'm sure that we'll make the most of this opportunity.
Well, thank you, Javier, and thank you again for your support in this seminar as well. So yeah, really appreciate it. Thanks. And
Okay.
thanks
Thank you.
everyone.